Okay, so I will continue my discussion on the EM algorithm. So to wrap up what I said and to clarify the message I had in the last lecture. So basically, the EM algorithm is a general approach for handling the cases. Maybe let me just write it again. So the EM algorithm is just a general approach which is applicable when you can easily write the complete likelihood and obtain its MLE. So it's easy to write the complete likelihood. So previously we wrote this as the, let me see, we wrote it as the f x z given our theta, right? So x is the feature vector. In our case, z is the label, observation label. So this is easy to write down and obtain the MLE. Theta hat MLE. So this is easy, but it's difficult to write the actual likelihood, which only depends on the observed data, f, x, theta. So x is the n observations p-dimensional feature vectors, our data. And as we said, even though we could use brute force integration to consider all possibilities of z, right? That's 2 to the nth possibilities, but that's too difficult. So this is where the EM algorithm gets into play. So basically in the E step, the E step is to find a lower bound of this fx theta. So let me denote this as L theta, a lower bound of L theta. Okay. And we actually showed that the lower bound can be obtained by taking just expectation with respect to z, okay? Z may follow any distribution, and its expectation of this ratio, or maybe I meant by that, it should be the L, small l. So the small l is the log likelihood. So we find a lower bound of the log likelihood as this thing. So it's basically, we have this log here of the fx z theta divided by some distribution of z. So I'll just call that qz. Okay, we said that we can use the Jensen's inequality to go here. So this is just by Jensen's. Okay, and qz can follow any distribution with density q. This is it. And then what we will say is that how can we satisfy the MM algorithm, which means that the lower bound must be equal to the log likelihood function at the current value theta t, to make this L theta t at the current value equal to the lower bound. Okay, so to achieve that, then at theta t, my bad, t should stay here. So theta t on both ends. So we need to have the what's inside the log, this one, to be a constant. We need the equality condition of Jensen's. So that is actually this, because we are in Jensen, we're swapping log and expectation, right? So when we can swap it and still have equality, it's what's inside here, the ratio. This is a constant with respect to z. In other words, the randomness of z will not affect this term. So no matter what value z takes, this term will stay as a constant. Then for this, we can show that the qz is basically given this joint distribution of x and z, it's basically the conditional distribution of z given x and given the current value theta t. Okay. So the reason is because if you set qz to that, then the ratio, because this ratio becomes, if I change qz to this, okay, it becomes just fx only given theta t. So this doesn't involve z anymore. So that therefore it's a constant with respect to t. Z is gone. So that's why for this tangency requirement, as well as the lower bound, we can, in the E step, we just find the lower bound as, so we find the lower bound of our target, the log likelihood function, as the expectation. Here, the expectation for z is specified. Z is specified to have the distribution as the conditional distribution of z given x given theta t. And this conditional distribution is actually from the joint distribution of x and z given theta t of this ratio, log fxz. Please note that here we are still having theta, because the theta is the same theta as in our log likelihood, the same argument. And it has nothing to do with the current value. The current value is only used to specify the distribution of z as this conditional distribution of z given x and theta t. So we satisfy the tangency of the lower bound. Okay, qz. Oh, I should write fz given x and theta t. Okay, that's the E step. So we basically find this minorization lower bound for the MM algorithm, right? This is a special case of the minorization lower bound in the MM algorithm. Then we maximize this lower bound. So in the M step, our goal is to find the theta to maximize this lower bound. So we move to the next value, theta t plus 1, right? So theta t plus 1 should be arg max theta of this term. So this term should be what we try to maximize. But then we realize one thing, that is we can write the log ratio as equal to log of the numerator minus the log of the denominator. And because the log of the denominator doesn't involve theta at all, so this will not affect the maximization. So therefore, this argmax is just equal to the argmax of this log numerator inside expectation. So expectation z given x and theta t of log f x z theta, right? And this is what? Inside the expectation, it's actually our log complete likelihood. So that's why, given the application domain of EM algorithm, it's easy to find the maximizer of this complete log likelihood, right? We use that. And so that can give us the update for the M step. The only difference is that we have this expectation of z given x and theta t outside of this log complete likelihood. So therefore, we need to move it into this sum. So sorry, into this log complete likelihood. So I was saying that for many special forms of the complete log likelihood, like in our Gaussian mixture model, so for many cases of this log complete likelihood. Okay, so for example, like the cases we have seen, it's like the summation I from 1 to n, like zi times something plus 1 minus zi times something, right? So this is the likelihood form, log complete likelihood form for our Gaussian mixture model. This is for GMN. So for cases like this, if you move the expectation inside the summation, you can just put expectation around each zi. So therefore, you can simplify this, z given x and theta t, this conditional expectation of the log complete likelihood. For this may be equal to a simpler form. That is, you can get expectation inside the log likelihood just around z. Okay, so this is the complete log complete likelihood with z replaced by this conditional expectation. And although z itself is not observed, but this conditional expectation is computable given the x and given the current parameter theta t. And with that, then you just maximize this in the M step using the MLD result. Okay, so I think for today, I'm just going to go through this EM algorithm in the Gaussian mixture model case, so everybody can understand how the algorithm operates on the operation level. You know how the iteration goes. So for this, I will go to use this thing. Okay, so this is the EM algorithm. I'm going to maximize the log likelihood of Gaussian mixture model for the incomplete case. We don't observe z1 to zn, but we just observe x1 to xn. So in the tth iteration, let's say that we assume the 5 parameters we're interested in estimating. This is the proportion of class 1. This is the mean and variance of class 0, mean and variance of class 1. Okay, so I should say the sigma 0, sigma 1, their standard deviation, their squares are variances. So then the first step, since this is the case where we can just put expectation around each zi in the complete likelihood. So the first step in the E step is to compute the conditional expectation given each zi. Okay, so let me restate this Gaussian mixture model example. So in this example, we have xi given zi equals 0, following normal distribution, mean 0, variance sigma 0 square. And xi given zi equals 1, following normal distribution, mu 1, sigma 1 square. And finally, the probability of zi equals 1 is equal to p. So this is the whole model, and we have 5 parameters. With those 5 parameters, we can fully specify this model. So given this model, we can derive the joint distribution of xz as well as the conditional distribution of zi given xi and some current parameter value. So let me say that I denote theta as just the 5 parameters I have here. So usually we use the column vector for vectors. So p mu 0, sigma 0 squared, mu 1, sigma 1 squared. Okay, so theta just denotes these 5 parameters together. So from this model, what I can write about for this conditional distribution of Zi, taking value 1, since Zi only takes 2 values, it's a Bernoulli random variable. It's a Bernoulli random variable with probability P. So the conditional probability that Zi takes value 1 given Xi and theta. So here, one thing I want to say is that, so for I from 1 to m, Xi, Zi, they are all IIDs. So they're all from this distribution and they're independent. So therefore, the conditional distribution of Zi only depends on Xi, not other X's. So in this case, I'll just directly write down this formula. It's based on the Bayes rule. Okay, so it will be the joint distribution of Zi equals 1 and Xi dividing by the marginal distribution of Xi. Both are given theta. So in this case, I can write it as just the normal density for this one class, okay? So it's just Xi minus mu I squared. This is the normal density from this part times that Zi is equal to 1. Okay, that's the numerator. For the denominator, I'm copying the numerator for once. Plus the case when Zi equals to 0. Times the chance that Zi equals to 0, 1 minus P. So this is the formula we are going to calculate for this conditional probability of Zi equals 1 given Xi and theta. So I would denote this complicated formula just by, let me see, since it depends on both Xi and theta, right? So I would just call this thing, let me see, I'll just call it eta I, a function of theta, because whenever I change theta, this will change. And eta I, the sub-index I, means that I'm talking about the ith observation. Here, Xi is the same Xi, regardless of theta. Okay, I had this notation. So from using this notation, we can also see that using the property that Zi is a Bernoulli, only binary values, we have the expectation of Zi given Xi and theta equals to this probability. That's the nature of Bernoulli. And this equals to eta, not eta, psi I theta. Okay, so this is the basis. Then in the E step, right? So in the E step, because we know in this case, our expectation of this log complete likelihood is ultimately the log complete likelihood with Zi's replaced by these conditional expectations. So in the E step, given theta t, the current value, we just compute these things. The psi 1 theta t, this is the expectation for Z1, to psi n theta t. This is the condition expectation for Zn. We have that for each Zi. And in the M step, we would take the MLEs, use the MLE formulas of the complete likelihood, which is what we had computed before, and replace Z1 to Zn in those formulas by what we did in the E step, by this psi 1 theta t to psi n theta t. Okay, so if you still have some impression about those things, So basically the theta t plus 1 is now updated as those values. So the pt plus 1 is the proportion of ones. It used to be just the average of z1 to zn. Now I'm going to replace it by the average of psi 1 to psi n computed at the current value of theta t. Okay, and for mu 0, the mean, normal mean for the class 0, it used to be the average of the xi's for which zi equals to 0. That's how we compute it. So we're going to just replace zi's by this psi I theta t. So it'll be summation I from 1 to m xn xi, right? It used to be xi times 1 minus zi. Now we're going to replace 1 minus zi by 1 minus psi I theta t. And for the denominator, it used to be the sum of 1 minus zi. Yep. Aditya, what's your question?
I just wanted to ask, so the reason that that conditional expectation is the psi is just because of the Bernoulli property, right? Like just because z is Bernoulli, or is there any other reason why we did this?
So the reason is zi is Bernoulli. So that's why this expectation is equal to the probability zi equals 1.
Okay, perfect. Thank you.
Thank you. Yeah. Okay, and used to be, the denominator used to be the sum of 1 minus zi. Now I replace it by 1 minus psi I theta t. Okay, so that's mu 0, the new value for mu 0. And then for sigma 0 squared, okay, this thing t plus 1. We used to have it just as for the zi's that are equal to 0. For those, we compute the average square distance between each xi, and that center. So we're going to do it. So here it becomes xi minus mu 0, the current center, t plus 1 square, times that it used to be 1 minus zi because we only consider zi equal to 0 cases. Now we replace it by 1 minus psi I theta t. Okay, that's the numerator. Denominator is the same as the above. Okay. All right, so finally, I will just write down the 2 other parameters for class 1. And I think you should also be able to do it yourself by following what we did above. Right? So that's it. That's the M step. We are just using the 5 MLE formulas from the log complete likelihood. And in those formula, we replace the unknown Z1 to Zn by what we computed in the E step, which you can regard as the imputed values for Z1 to Zn, given X1 to Xn and the current parameter value, theta t. Okay. So then with these values, you go back to the E step to compute. Now you're going to have psi 1 theta t plus 1 to psi n theta t plus n. And then in the M step, you're going to get theta t plus 2. And you just iterate these 2 steps until your theta value converges. Okay, so does this make sense to people? How the EM algorithm works? So you can see that it's a special case of the NM algorithm. Here we just give you the minorization as the expectation of the log complete likelihood, we ignore that denominator. We just talk about numerator. And expectation is with respect to the conditional distribution of z given x and theta t. Okay, so I think that's all. That's all I want to say for this EM algorithm. And this concludes the model-based clustering part. So recall that we spent quite some time on the clustering part, unsupervised learning, clustering, right? So here our data is only x1 to xn. Each xi is a p-dimensional vector. So in our biological genomics example, we can regard each xi as our ith sample or our ith cell in our single cell data, and the p features as our p genes. Or if you look at ataxic data, the P could be P genomic regions. So I want to say something about the final project because I received many interesting ideas and questions about what to do. And I want to say that one important advice, maybe general for everyone, is try to do enough literature research before you settle down on what you want to work on. Since this field is very, very popular and very crowded, so it's very possible that the idea you have some interesting work out there in the literature. So you don't want to miss that. So, and also I want to emphasize this is a class project, so don't take it as your dissertation research, right? So the scope should be quite reasonable. So therefore, if you do some reasonable literature review and summary, I think that's good enough. So I'm not saying that everybody has to invent a new, completely new algorithm. That's definitely beyond the scope. Okay. So, all right. So that concludes the clustering part. We started by talking about algorithm-based approaches, including the k-means, hierarchical, and also the related, say, spectral clustering and the tight clustering, which were just based on the k-means, and also the consensus clustering. So those kind of things are all algorithm-based. They don't assume a distribution of your data. And later, we talk about this Gaussian mixture model, which is the most classic model-based way of doing clustering. And you can imagine that if your data don't follow a Gaussian distribution, you may replace Gaussian mixture model by some other mixture model, right? For example, in single cell data, if you assume each cell has a P genes, and then each gene, if you don't want to assume that it follows a normal distribution, normal means Gaussian, you may want to assume that if you work with counts, right, you may want to assume that my gene follows a negative binomial distribution, the distribution we talked about, and then you can modify the model accordingly. But one thing I want to say is that Gaussian is a very nice thing in that if you have P features jointly Gaussian, then each feature is Gaussian. And any linear combination of features is still Gaussian. That's a unique property of Gaussian distribution. But for some other distributions, you may not have this. So that therefore it's a little more difficult. But yeah, that wraps up what I want to say about the clustering. So do we have questions before I move on to our next topic, which is the, let me see, which is the dimension reduction problem, which is another part of unsupervised learning. So given that in our biological data, usually it's high dimensional, right? So if you regard one set of dimensions as your samples, for example, cells, the other set of dimensions as your features. So for single cell data, you have seen both dimensions are big. So, but do we really need such big dimensions to capture the information in our data? Maybe not. So dimension reduction then kicks in. It's a way to reduce some redundant dimensions, but still retaining the major key information in your data. Okay, so that's my next topic. Can we move on if there are no questions? All right, so now let's talk about the second type of unsupervised learning. Okay, so it's still unsupervised. So part 2, this is dimension reduction. Okay, and this is sometimes referred to by other names, like some people may call it, I would say, visualization or embedding. Yeah, I think embedding is the term. So, and if you just set the reduced dimension to two dimensions or 3 dimensions, you may use the reduced dimensions for visualization. Okay, so these are all connected. But just the same as our clustering setting, here we still have n observations to start with. And we denote them by x1 to xn as always, and each is p-dimensional. So recall that for the clustering problem, we try to divide or partition the n observations into a few clusters. That's the task there. And here the task is that we want to find a smaller dimension, smaller than p, to still present my n observations. Q. So find, let's say, I'll just call it, maybe, is it good? Should I still call it Z? To be consistent with my notes, the one I posted just CCLE on the homepage, probably I'll stick with that, but don't confuse these Z1 to Zn with the previous labels. So you want to find low dimensional. This is what we call embeddings. Embeddings is a machine learning term. So they mean that we want to find another n vectors. Each are, let's say, d-dimensional. Is that good? Or maybe I just say r-dimensional with r much less than p. So in other words, you are interested in finding the z1 to zn, and you hope that the z1 to zn, despite being in a lower dimension, r dimensions, instead of the original p dimensions, but they can largely preserve the signals in x1 to xn that you are interested in. Okay, so that's it. So we will start with the most classical method everybody must have heard of, PCA. So principal component analysis is always the method to talk about when we talk about dimension reduction. Okay, I think operation-wise, many of you must have used PCA before, right? You know what the output is. But today we're going to give you a deeper understanding about why PCA works like this and what's the underlying reason behind the algorithm. So first thing, which is quite fun to point out, is the spelling. So a lot of people may misspell it as PLE, but it should be PAL. You know, in English, these two words have the same pronunciation but different meanings. So this is principal component. So this is an adjective instead of a noun. All right, so one way to consider PCA is that if you define the variance among your observations, right? So you can write for your data, like here, the n observations. So if we, just for simplicity, we can consider, or maybe not. Okay, I'll do that later. But for now, let's think about the variance in the n observations. So we know how to calculate the variance in each dimension, right? And we can sum up the variance across dimensions to be the total variance. So this will give me, okay, a double summation. So let me see. Let's say J from 1 to P, I from 1 to N. Then in each dimension J, I want to take my Xij minus the mean in dimension J. I call that Xj bar square. Okay, so to be specific, Xij is just the jth element of Xi. Okay, and for this X dot J bar, I mean that I'm taking the average of all the Xi's in this dimension J. That's the average. So this is the total variance in the original data. If I write the total variance in the new data, in the low dimensional embeddings, then it will become, say, I will say Xij k from 1 to r, I from 1 to n, z I k minus z dot k bar square. Okay, so what we want to say is that basically for the PCA, right, you can compute your variance in this way. In the new data, you want to compute the variance in this way. And what if your goal is to preserve the variance as much as possible, right? Or I want to say, one thing I didn't say specific is here. If you think about your original P dimensions, okay, so this is the case. So if two dimensions are completely replicate of each other, so they're equal, then those two dimensions can basically be represented by just one dimension, right? There's no reason to keep both. So in that case, even though both dimensions will contribute to this total variance, but that's not the thing you're interested in. So therefore, for this one, for the low dimension embeddings, our hope is that with the R dimensions uncorrelated as much as possible. This is one thing. So we don't have that redundancy issue. And furthermore, we want the Z11 to Zn1. So the n observations in the first new dimension preserves the most variance. Okay, so that's our overall hope. We want to find R dimensions that are uncorrelated with each other, despite that the original P dimensions may have some strong correlation, and that's redundancy. And second, we hope that there is some order in the new dimensions 1 to R so that the first new dimension preserves the most variance. Okay, so PCA assumes PCA is a linear dimension reduction. So in other words, what we would have is this. So basically for each observation, let's make it as an example. So let's say for each observation Zi1 in its first dimension, we want it to be a linear combination of the original P dimensions of X1. Okay, Xi, sorry. So we want this to be, okay, I'll just write it as some coefficient 1, 4 times Xi1 plus phi 2, 1 plus X times Xi2. Right, plus phi P1 times XIP. So XI1 to XIP are the P values in my original vector Xi. And I give each dimension a coefficient called phi something 1. Okay, the first sub-index in phi indicates the dimension. The second sub-index indicates that I'm talking about my new dimension 1. So basically, the idea is that if I have the second dimension, I will write as phi 12 xi1 plus phi 22 xi2 plus phi p2 xip. So the second index always indicates the new dimension, while the first index in phi is about the old dimension. Okay. So, and our goal is to make sure that the new dimension 1 has the maximized variance. Okay, so now I'm going to say that if we simplify the problem so that if for each j, we have xij sum up to 0. That means in each O dimension, if we center our original data so that the mean and the sum is 0, then you can see that by this linear combination thing, a natural result is that for every dimension, new dimension k, zik is also equal to 0, the sum. So now k is equal to 1 to r. So this centering can make my following discussion easier, because when we compute the variance, we just set a center to be 0 instead of worrying about average. Okay, so the goal is to maximize this thing for each zi. Maximize zi1 square, I from 1 to n. That's our goal. So because I set the center to be 0, this is just, I ignore the n. Okay, so if I just divide the n back, so this is just to achieve the maximize the variance of n observations in the first new dimension. That's our goal, to find the first dimension for the PCA. How do we achieve it? Okay, so now I am going to use linear algebra. So here I just talked about one observation, but now when I'm going to vectorize it to go to, say, I'm going to go to the vector matrix notation. Okay, so what I'm going to do is I'm going to stack these things. I call it Z. Okay, by stacking it, I have Z11 to Zn1. Okay, so I stack the n observations in their new dimension. And then you can see what? If you're familiar with the linear algebra, then you can recognize that this is basically, based on what I wrote here, the first line here, it's basically equal to this whole matrix, which I write as x11 to x1p. So the first observation is in the first row to xn1 to xnp. Okay, it's this matrix I multiply by a column vector specified by these. Okay, I can put phi 11 to phi p1 here. So if you check the math, this first row multiplies the column will give me the z11, and that's corresponding to the first line of equation there. Okay, and if you recall, this is what we store our data, right? Our data matrix with the rows as observations, columns as features. So this is our data matrix X. And this is what we call the loading vector. This loading vector 1 is the first loading vector that projects the original P dimensions into our first new dimension. So for this loading vector, I call that phi 1, which is P dimensional. Okay, so that's it. So basically we simplify the vector Z as X times phi 1. Okay, now the objective. The objective, previously we write as sum of max zi1 squared, I from 1 to n. Now, you know, this can be just written as the inner product of z with itself, right? So this is basically max z transpose times z. That gives the sum. Okay. And now I'm going to put z equals x times phi 1 back to here. So you will see I have phi 1 transpose x transpose times x times phi 1. That's the new objective. And how do we find a max, right? What are we looking for? we are basically looking for the p-values in the loading vector 1. That's the values we're looking for. So therefore, it's actually about finding phi 1 to maximize this whole objective. Okay. And one more thing I want to say is that I don't know if you have realized that if I just write down this max without putting any constraint on this phi 1 vector, it doesn't make sense because I could just easily multiply each element by a very large constant, and that constant will go into the sum here. So there's no upper bound on that, right? To basically make sure this optimization problem is meaningful, we need a constraint on the size of phi 1. And a reasonable constraint is to assume that phi 1 is a unit vector, which means that it has the unit L2 norm. Or in other words, we can assume that with constraint that phi 1 transpose times phi 1, so it's inner product with itself, which is basically what we write as the phi 1 L2 norm square. Or you can spend it as the summation j from 1 to p phi j1 square. Okay, that's the L2 norm square. We set this to be 1. So this can ensure that the magnitude of phi 1 cannot be infinitely large. And because that magnitude will go into the variance here. Okay, so then this optimization problem becomes how to find phi 1 to maximize this and such that phi 1 transpose phi 1 is equal to 1. Under this constraint, how do we do this optimization? And one technique for doing that, maybe some of you have heard of this, maybe not, but I'm just going to introduce it. It's called a Lagrange multiplier. So the idea is to put this constraint as part of your objective function for optimizing. Okay, so basically use this technique. We change this maximization problem to minus some, we introduce some constant lambda here, and then we add this. Okay, the reason we could do it is because if this constraint holds, right, then the second term will be 0, so it would not affect the result. Okay, and then what we can do is that we would use our gradient approach to find the maximizer. Okay, so we take the gradient against this vector phi 1. Okay, since the phi 1 is a vector, so then the partial derivative against each component will give us the gradient. And we want to set the gradient to 0, right? So now this is the matrix calculus. How can we take the gradient of that? So the key is to bear in mind the dimension. Okay, so if you assume the gradient to be a column vector, then for this one, right, this one is just a scalar. It's the scalar value. So for the scalar value, take the gradient against a vector, then the gradient, it should be a column vector. So here we actually, I'll just give you the answer. The gradient here is 2 times x transpose x times phi 1. So this thing, you can easily verify that it's p-dimensional. Okay, this is a p-dimensional column vector. And for the second part, we are going to have -2 lambda phi 1. Okay, so if you want to set this to 0, right, set the gradient to 0, and you will see an interesting result. That is, if you just move the second term to the right and cancel the 2, you have x transpose x times phi 1 equals lambda times phi 1. What is this? This is our definition of eigenvalues and eigenvectors of this matrix, x transpose x, right? So you're there. So basically, you see that you need to have, so lambda is an eigenvalue of this X transpose X, and phi 1 is the corresponding eigenvector. But we know that if this matrix has rank greater than 1, then it may have more than one eigenvalues, right? But which one would we pick? Now let's go back to our objective function. So you can see that based on this relationship, this is the key for PCA. So if we want to find the maximizer of right, you put this inside, then you will see it becomes lambda phi 1. And lambda is a constant, it can go to the front. And phi 1 transpose phi 1 is 1. So it's just to maximize lambda. Okay, so then the problem becomes among all the eigenvalues of this matrix, you want to pick the largest eigenvalue. Okay, so that solves the problem. So that means lambda is the largest eigenvalue of X transpose X, and phi 1 is the corresponding eigenvector. So we find the first new dimension. So this is the basic idea of PCA. Okay, and then for the second new dimension, you are going to add one more constraint. That is, the second new dimension must be uncorrelated with the first new dimension, and you still want to maximize the variance. And then you can show that the loading vector for the second new dimension would correspond to the second eigenvector of this whole matrix. So that's why the whole PCA idea becomes Eigen decomposition. So to find PCs, right? We do PCA, we want to find PCs. So the key is Eigen decomposition of this matrix, X transpose X. Okay, so what can we get out of the eigen transpose, eigen decomposition? Actually, in linear algebra, the standard way to write eigen decomposition is this. So let's say that we write X transpose X, we do eigen decomposition. And also please note that eigen decomposition is only applicable for squared matrix. Okay, here it's squared matrix. And also because the special nature of X transpose X, it's actually positive semi-definite. So that means when we do the eigen decomposition, the eigenvalues are all non-negative. And that's also important here. So based on the eigen decomposition, we do that, and we can write it as usually in this way. So this is a P by P squared matrix. So we will write as a V times lambda times V transpose. So it's the same V on the both sides, and lambda itself is just a diagonal matrix. Okay. So basically, if we do that, then we can expand it as, so maybe I'll just do it. So I can just write it as, write down the, then this is P by P, everything is P by P. Okay, so I'll just write this out using our notation. So this is basically our phi 1, the loading vector for the first dimension, to the loading vector of the pth new dimension. If we don't do reduction, we just do a rotation and also extension or subtraction or extraction. So we are just going to get new p dimensions for this. So I'm lining them column by column times a lambda matrix. I call it lambda 1 to lambda p. So they are sorted in a decreasing order. Okay, finally, the transpose of that, it would be phi 1 transpose. Okay. So with those loading vectors, one more thing I want to say is that if you think about it, the reason I write it this way is because this is a very fun fact of linear algebra. So we know that when we do matrix multiplication, we could do a row multiplied by column, give us a scalar, right? We have that. But another way to do is that if you look at your matrix as a column multiplied by a row, that's called outer product. That can give you a matrix. So basically, I can write this as lambda 1 phi 1 times phi 1 transpose plus to up to lambda p phi p times phi p transpose. And each is a p by p square matrix. Okay, this is an important way to look at this matrix X transpose X. So basically, we decompose it into P matrices, and each matrix has rank 1. The reason is that this matrix, the column is the outer product of one column times one row. Okay, so with those, then finally, we want to do the Eigen decomposition, right? So with those eigenvectors available, then the PCs are just, the projections. Okay, so let's see, we have X transpose X has eigen values lambda 1. Okay, it's possible that some of the later lambdas may be 0. That's possible. So like the number lambda 1, the number of non-zero eigenvalues depends on the rank of X transpose X. Okay, so this matrix may not be full rank, and this rank cannot be greater than the minimum of N and P, the 2 dimensions of the original matrix. Okay, so then when you decide to keep, when you say how many PCs do I want to keep, right? It depends on how many dimensions you want to go down in the eigenvalues. So I just write the corresponding eigenvectors as phi 1 to phi p. Okay, so let's say that we want to have R new dimensions, right? That's the dimensions of our Z1 to Zm. So Z1 to Zm, they are each R dimensional. And then what we can do is simply Z1 is just the, I would say, it's the vector, right? So it's the R dimensional vector. So what I would say is, maybe let's just do this. So I put the Z matrix Z as Z1 transpose to Zn transpose, like here. Okay, so it's M by R. Each row is an observation, each column is a new dimension. And then what I can do is that this is just equal to the original matrix, the X matrix, which is M by P, P columns for the P original features, times this thing, phi 1 to phi r. So this is a P by R matrix. You just keep the top R eigenvalues corresponding eigenvectors, align them here, then that's what you get. So in other words, we can say that this is our PC1. PC1 is just this vector Z11 to Zn1, which is equal to x times phi 1. That's PC1. And if you go to PCR, the rth PC, it's the vector Z1R to Znr. So the rth column of Z here, which is equal to x times phi r. Okay, so here I want to make a distinction. That is, each PC and loading are two different concepts. So PC is the X matrix times the loading vector. But in some contexts or some papers, people mistakenly called the loading vectors as PCs, but that's not correct. So the loading vector doesn't involve your n observations. It's just a p-dimensional vector. Here, phi 1 is a p-dimensional vector. So phi 1 is Rp, x is n by p, right? So let me see, phi 1, yeah. Okay, I think maybe I need a transpose here. It should be p by 1. That should be correct. Yeah, this is Rp p by 1. Sorry, so this is Rp. And this is n by p. Yeah. So basically we say that the loading is called a loading vector 1, that's phi 1, and loading vector r, that's phi r. Right, so I hope we can be more careful about the language we use here. So when you talk about the n observations or your n data points and their embeddings, you are referring to PC1 to PCR. But when you talk about how the new dimensions are constructed from the original P dimensions, you talk about the loadings. Okay, is that clear for PCA? So based on that, then how do we choose the number PC? That's quite interesting problem. And I don't think there's an absolutely optimal answer. The most popular way is still do the elbow plot. So you would try to compute this, so PVE, okay, percent of variance explained against the number of PC. So for example, 1, 2, 3, right? So basically, the number of PCs to explain the proportion of variance explained is just simply this. So PVER. Now we can see that, oh, sorry, this is something I want to emphasize. So realizing this Eigen decomposition connection to PCA, right here we see that the variance to be maximized is actually lambda. So essentially here, lambda 1 to lambda p corresponds to the variance in each new dimension. And this is the key information. So I want to say here, the variance 1 in the first PC is simply lambda 1. And the variance in the rth dimension is lambda r. So therefore, the percent of variance explained is simply by this, right? The number of PC is simply lambda r divided by sum of lambda 1 to lambda r. Oh, wait, sorry. It's actually this sum of lambda j from 1 to p. Yeah, So that's the total variance in our data. So the total variance in our data is actually captured by that diagonal matrix after Eigen decomposition. So then the proportion explained by the rth dimension is just that corresponding rth diagonal entry over the trace of the lambda, the diagonal sum. Okay, so then the proportion of variance explained. So for example, usually because you order the PC by decreasing variance, right? So the first one will have the largest PVE and it probably decrease here, right? So if you see a case like this, then you see, after maybe PC1, the other PCs don't make much contribution. Then I may decide to stop at PC1. One dimension is enough. But if you see, PC2 is still quite strong, and then PC3 becomes weak. So you're going to use that visual inspection to find where you want to cut. And of course, there's no absolutely correct strategy because it really depends on what you consider as the biological variance in your data versus the noise variance. Because some of the small variances, you have to decide whether you think they are noise or biological. It's case by case. So for example, if the PVE plot looks like, if it looks like gradual decrease, so you have a lot of strong eigenvalues, then the call is less obvious. And actually that's the case in single cell data. So like if you check the Seurat pipeline, I think they typically use 20 PCs or 30 PCs as the input for their downstream analysis. So basically, they are using the PCs as the new data matrix instead of the original X. So they're using the Z for their downstream analysis. It's N by 30 or 20 instead of N by, say, 20,000, a very large number of genes. So, but I just say that if you check the literature, you can see there's some new work coming out about how to find the number of PCs with what they consider as a reasonable PC, and how can you call some of the eigenvalues as coming from noise instead of real biological signal. I think this is a very interesting problem. And if you want to have some more understanding of it, I think there's a field called random matrix theory that specifically studies the eigenvalue distribution about random matrices. So that's something that could, I would say, shed some future light on this topic. And I think that's very interesting. Okay, so that's all about PCA. I want to say, so related to PCA, another technique I will introduce as our second dimension reduction approach is called multidimensional scaling. MDS. Okay, so I would like to give you a first hint is that the classical MDS is actually equivalent to PCA if the distance is computed by Euclidean distance. So that's the first hint. But what's different between MDS and PCA is that here the input is no longer an N by P data matrix, but an N by N distance matrix. It could be a distance matrix or just some dissimilarity matrix. So we call that D. And it's N by N. And we denote its entries as Dij. Okay, so Dij is basically the distance or dissimilarity between observations I and J. That's Dij. This is your input. And given such a distance matrix, the question is, do you want to find, how can you find some embeddings of the N observations for which you don't have the original P vectors? So the output is that we want to find, so let me still stick with my previous notations, Z1 to Zn, okay, in R dimensions such that the Euclidean distance between Zi and Zj in the R dimension, this is the Euclidean distance, is approximately Dij. This is the goal. So try to find the embedding to preserve the distance. Oh, one more thing. I think I forgot to say that, but it's quite important about PCA. So, you know, in the theory derivation, right, we assume the data, every dimension is centered. So that's why in PCA application, when people do the PCA, there's an option in R called center, true or false, scale, true or false. You need to specify that. And I think the default is that the centering is true, scaling is true. So that means that your data input X will have its every column centered and standardized to have variance 1. But whether that's always the thing you want to use, it's case by case. So for example, if your P features are P genes, and you believe that some genes have larger variances and that's important, if you want to preserve that, then you don't want to standardize your genes to have variance 1. So that's the consideration you need to have. So whether you want to, you need to do standardization. But in some other, say, social stats context, for example, your P features are P characteristics that are measured in completely different units. So in that case, standardization is a must. Otherwise, the numbers are not comparable. So that's the first consideration. Regarding centering, I would say in most cases, you want to standardize, you want to center your data to have mean 0, unless you have some strong belief that the mean is already 0, the population mean is 0, and your data is just part of the population. If you have that strong belief, then you can skip the centering step. Otherwise, centering step is also necessary. So maybe I can talk about this a little bit. So let's say that your data looks like this. You have 2 dimensions to start with. This is the origin, okay, 0, 0. And if your data looks like a scatter with no strong correlation like here, okay? So if you don't do centering, but you run PCA, then the first PC defined by the loading vector will actually be this way. So basically, loading 1 vector may have, say, equal coefficients from the first 2 dimensions. So this will be your PC1, and you're going to project your data to that. But if you do centering, okay, and you move your data to the origin like this with centering, then it's different. So the PC1 may not be that anymore. Okay, so in this case, because the 2 original dimensions are basically, you know, just uncorrelated to themselves. So in this case, the PC1 can just be a standardized version of the dimension 1, PC2 dimension 2. So you may not have that rotation anymore. So therefore, doing centering or not is crucial. But in most cases, unless you have strong belief that, oh, although my data are far away from 0, but I believe my data is already centered, it has been centered somehow before, then I don't need to do centering. Otherwise, you have to do centering as the standard practice. And regarding scaling, I think the key is whether your original P features are already in the same unit or not. Okay, so I guess I can stop here. And next time when we come back, we will talk about this MDS. So that will be actually on next Wednesday, because next Monday, I think is a holiday. So we will not have a class on that day. And so I'll see you on next Wednesday then. If you have any questions, you can stay in the Zoom.